What if fragility itself is not a weakness, but a language spoken by time? We might think of an interstellar body like Atlas breaking apart as it neared the Sun and see only failure, only disintegration. Yet if we rest with the thought a little longer, the image shifts. Fragility becomes a sign, a trace of what the object has endured. Just as old paper yellows and cracks but still carries words across centuries, a fragile comet may carry memory across millions of years. Now we are placed in a wide frame of space and time. Atlas came from far away, likely wandering for millions or even billions of years. In that scale, its life near the Sun was just a fleeting spark, a brief moment of visibility. The vast majority of its journey was silence, cold and invisible. To imagine this is to place ourselves in an immense archive, where shelves stretch not in meters but in light years, and where each fragment is a document shaped by endurance and loss. Let us stay a moment with the processes that shape this fragility. Comets are loosely bound collections of ice, dust, and minerals. They are not like solid rock, but more like snow mixed with soot, porous and delicate. As they travel near stars, the heat releases trapped gases, which push against the surface and cause cracks. Over time, pieces break away. This is why many comets fragment, and why Atlas dissolved so quickly in our sky. To compare, imagine carrying a frozen loaf of bread from deep winter into a warm kitchen. The crust cracks, steam escapes, and soon it is no longer whole. Nature works with the same quiet physics on cosmic scales. But we also remind ourselves of what we do not know. We have only a handful of interstellar visitors recorded. Most comets are never seen at all. With Atlas, the data are limited, blurred by distance and the speed of its decay. We cannot reconstruct every detail of its inner structure, nor its full journey through the galaxy. Absence of detail is not absence of story. It is only a pause, a gap in the record. And gaps themselves can be meaningful, just as silence in a piece of music is part of the rhythm. When we listen carefully, fragility speaks through indirect signs. Astronomers trace brightness over days, and the sudden dimming tells them of breakage. Chemical lines in spectra show water, carbon compounds, metals. These lines are like the ink left on a torn page, still legible even when parts are missing. Dust grains captured in Earth's atmosphere add another layer, each particle a micro-archive of conditions and forces. Together, these fragments allow us to guess at a broader history, though the outline is never complete. Let us now try a small thought experiment. Suppose we imagine Atlas not as an ordinary comet, but as a fragment of something once larger, shaped by energies beyond our current sight. It drifts for eons, weakened by radiation, by impacts, by slow erosion. When it finally enters our solar system, it breaks apart, scattering dust. Over thousands of years, that dust may fall through Earth's skies, settle in ice, or mix into sediments. Centuries later, scientists might study these grains, puzzled by unusual ratios of isotopes, unsure whether to attribute them to distant stars or unknown events. In this way, fragility becomes not an ending, but a transformation, a way for hidden signals to spread and persist. Now we pause gently and draw no hard conclusion. Fragility in comets is expected, natural, explained by heat and structure. At the same time, in its delicacy, it opens room for reflection. Whether ordinary or extraordinary, the breakage of Atlas invites us to see impermanence not as loss, but as continuity in another form. Pieces do not vanish. They change, they disperse, they whisper across different layers of space and time. In this quiet perspective, fragility is not a flaw, but a reminder that endurance often speaks softly, through cracks, through dust, through traces we may someday learn to read more deeply. What if the rapid fading of Atlas was not simply a weakness, but a message hidden in plain sight? When it entered the warmth of our solar system, it shone faintly for a short while, and then it dissolved. To many observers, this was predictable, almost ordinary. Comets are fragile wanderers, easily undone by the heat of a nearby star. Yet when we rest with the image, another layer opens. Its fragility may speak of long endurance, of countless ages past, of a body carrying silent burdens until the moment it could no longer hold them. In the vastness of space, scale stretches far beyond human memory. Atlas may have traveled millions of years through interstellar cold, its structure slowly altered by radiation and by the quiet impacts of dust grains. For most of that journey, it remained unseen, moving through darkness, neither burning nor breaking. Only as it brushed close to the sun did its fragility become visible to us, like an old manuscript finally taken out of storage, touched by light and falling apart at the edges. To understand why this happens, we may pause with the processes that shape such a body. A comet is often compared to a dirty snowball, but it is looser than a snowball, more like a frozen sponge, filled with tiny pores, ice, and dust mixed in a delicate balance. When sunlight warms it, the ice does not melt as water does in a cup. It sublimates, turning directly from solid to gas. These gases push outward, lifting dust, widening cracks, and sometimes forcing entire pieces to split off. This is why comets often leave trails, glowing as their surfaces unraveled. Atlas showed this process in an especially fragile way. Instead of resisting, it gave way quickly, its core fragmenting until little remained to see. We should pause to acknowledge the limits of our knowledge. The breakage of Atlas was observed through telescopes, but only for a short window of time. No spacecraft approached it, no fragments were collected. All we hold are blurred images, light curves that tracked its brightness, and a handful of models predicting how quickly its mass dispersed. The gaps are large, and in these gaps we must be careful. A single fragile comet does not prove anything beyond its own story. Yet its story leaves traces that extend beyond itself. These traces are not loud. They are quiet records written in light and dust. The pattern of its fading tells us when the breakup began. The direction of the fragments reveals the pressures at work. Even the color of the dust shines with chemical hints: carbon compounds, silicates, tiny grains of organic matter. All of this becomes part of an archive, stored not only in scientific papers, but in Earth's upper atmosphere, where some of the smallest grains may eventually settle. To move deeper, let us imagine a simple sequence. First, the comet fragments near the sun, scattering thousands of smaller bodies along its path. Next, many of these bodies are drawn outward, dispersed by solar radiation and the push of the solar wind. Finally, a fraction may drift across Earth's orbit, falling quietly as meteoric dust, captured in the polar ice or ocean sediments. Centuries later, scientists studying those layers may find a faint enrichment, perhaps an unusual ratio of isotopes, perhaps a pattern of organic compounds not common elsewhere. They might not connect it directly to Atlas, but in the silence of data, the comet's fragility would continue to speak. We may now soften into a careful pause. The disintegration of Atlas can be explained by natural physics, and that explanation is sufficient. At the same time, the speed and delicacy of its fading remind us that every fragment holds a longer memory than its final moment suggests. Fragility is not only loss, it is also a release, a way in which information once locked inside begins to spread. Whether ordinary or extraordinary, Atlas teaches us that what breaks does not disappear. It only changes form, scattering into traces that may one day be read as part of a much larger story.
What if the layers inside a comet are not only deposits of ice and dust, but also quiet pages of memory? When we picture such a body, we often think of a frozen surface glowing faintly in sunlight. But deep inside, there are structures that hold the record of time. Each stratum preserves the conditions of its birth and the changes that followed. In this way, a comet can resemble a tree trunk, where growth rings speak of seasons long past. The cosmic scale, however, stretches far beyond seasons. These layers may carry the imprint of millions of years, of encounters with radiation, of passages near stars, and of collisions with unseen fragments drifting through interstellar space. Now we are within a vast archive, one that does not write with ink, but with chemistry and texture. To understand how this works, let us pause with the mechanisms. A comet forms when dust and ice gather in cold regions far from stars. Over time, as more particles settle, layers build up. Pressure increases slowly, though never enough to make the body solid like rock. Instead, it remains porous, like compressed snow. Each incoming particle adds a note to the archive. Volatile materials, those that vaporize easily, become trapped in the deeper layers, sealed like letters in envelopes. When the comet later warms, these sealed gases may escape suddenly, leaving behind empty cavities or fragile shells. Such processes are natural, yet they also create irregular textures that may be misread or perhaps reinterpreted as scars. Here we must be gentle with our uncertainty. With Atlas, the interior layers are gone to us, dissolved before we could study them closely. No samples were captured, no spacecraft drilled into its core. We rely only on models, based on how other comets behave. This limitation is important. Without direct access, we cannot state with confidence what its layers truly contained. Still, there is a language of traces. The brightness pattern during its disintegration hints at sudden releases of trapped volatiles, which suggest layered storage. The dust composition, measured through spectra, showed both organics and minerals, implying that its building blocks came from more than one region. Even the way it broke, splitting rather than crumbling, points toward hidden inner boundaries, zones where material was weaker or differently structured. These boundaries are like half-erased lines in a manuscript, not fully readable, but clearly present. Now we may let ourselves try a thought experiment. Imagine Atlas beginning as part of a larger body, shaped in a young system long ago. It experiences a sudden burst of energy, perhaps a collision, perhaps an exposure to radiation beyond what we commonly see. Layers melt in places, then refreeze, leaving veins of unusual minerals. Ejected from its origin, it drifts through the galaxy. Over eons, cosmic rays alter some of its isotopes, marking time like faded ink. When it finally enters our solar system, we see only the outermost layer, brittle and faint. The deeper archives dissolve before we can touch them. Yet in sediments on Earth, tiny particles might someday be found, still carrying altered isotopic ratios, quiet signals of an event no longer visible. Whether or not such an origin is true, the exercise helps us appreciate fragility as testimony. We learn that layers, even if lost, leave indirect impressions in light curves, in dust spectra, in patterns of disintegration. Each is a form of language, waiting to be read with care. So we come gently to a pause. The idea of memory in cometary layers remains mostly speculative for Atlas, since it vanished before deeper study was possible. Yet the concept is not empty. Comets are time capsules. Their structures hold more than just frozen water. They hold a record of conditions spanning both place and era. To approach them is to approach a kind of layered library, where each fracture and release of gas is like a page opening briefly before crumbling. In the quiet of that image, we are reminded that knowledge often comes not from what remains whole, but from what falls apart and still leaves traces behind.
What if the universe itself once bore conflicts so immense that their remnants drift quietly among the stars? When we hear the phrase cosmic war, the mind may lean toward noise and destruction, but here we will soften the idea. We are not speaking of battles like those on Earth, full of sound and fire, but of energies colliding, of matter reshaped, of structures unmade. On galactic scales, even natural processes can appear like conflicts. Stars crash together, black holes tear apart suns, shock waves ripple through clouds of gas. To us, it may look as if the cosmos has been fighting with itself since its earliest days, though in truth it is only following the laws of physics. Let us place ourselves gently within this wider context. The galaxy is not still. It is dynamic, always shifting, always reshaping. Planets form through collisions, moons are carved by impacts, asteroids carry scars from endless encounters. Some are violent, some quiet, but all leave marks. Now we pause to notice that the line between accident and intention is delicate. When we imagine war, we usually imagine intent, design, choice. When we look at space, we see events that could, from a distance, resemble those same outcomes, but without conscious cause. The uncertainty lingers, and here we must rest with it. To understand the possible mechanics, let us think simply. When two large bodies collide, heat is released, fragments scatter, trajectories change. When intense radiation sweeps across a region, molecules can be broken apart or rearranged. Over millions of years, debris spreads, settling into new orbits or cast into interstellar space. This is how both ordinary collisions and any imagined deliberate conflicts would leave traces. The universe does not preserve the motive, only the effect. Now we remind ourselves of the limits of knowledge. We cannot separate with clarity what was natural from what could have been intentional, if such intentions ever existed. Our tools detect light, spectra, patterns of motion. They do not tell us why. Absence of clear markers is not proof that nothing happened. Yet presence of anomalies is also not proof of design. We are suspended between these two uncertainties. Still, the cosmos speaks through indirect signs. Craters on planets are one such language. They tell of past impacts, each one an entry in the archive of the solar system. Meteorites that fall to Earth carry unusual isotopes, signatures of formation in environments we can only reconstruct through models. Even the distribution of asteroids in belts may whisper of events long past, perhaps chaotic beginnings, perhaps more structured disruptions. These are data, quiet markers of history without commentary. Let us try a small experiment of thought. Imagine a young galaxy where life has not yet spread widely, but energies are abundant. Massive structures form, and some perhaps are shaped or redirected. A collision occurs, scattering fragments. These fragments drift, some ejected entirely from their system. Millions of years pass, and one fragment, altered and fragile, crosses into our solar system. To us, it appears as an ordinary comet, faint, breaking apart under sunlight. We note its trajectory, its spectrum, its fragility. But hidden within its dust may lie altered minerals or unusual distributions of elements, silent traces of an ancient event we no longer recognize. In this way, even if a war once occurred, its story reaches us only as quiet chemistry, as fragile memory embedded in matter. From this, we move slowly toward a pause. The notion of a cosmic war is vast, heavy, but here we allow it to soften into metaphor. It is less about armies and more about the meeting of forces, less about conflict and more about transformation. Whether by accident or by design, the universe leaves traces in the form of scars, layers, and drifting fragments. Our role is only to read them with humility, knowing we cannot always tell the difference between chaos and intention. In the end, what remains is not the clash itself, but the silence afterward, carried gently through time in the fragile archives of stone and ice. What if the quiet archives of a possible ancient war are not written in words, but hidden in fragments of matter drifting through the cosmos? When we speak of archives on Earth, we imagine libraries, shelves, drawers filled with records. In space, the shelves are debris fields, the drawers are meteorites, and the records are locked in isotopes, minerals, and dust. Unlike paper, these archives are not meant to be read quickly. They endure for millions of years, waiting for encounters that may never come. We place ourselves now in this scale, far beyond human lifetimes. The solar system itself is about 4.5 billion years old. In that time, countless collisions have filled it with remnants. Each asteroid belt, each comet cloud, is like an open archive, though one without order, without index. If something unusual happened long ago, whether a natural catastrophe or something we would cautiously call deliberate, the traces might still be hidden among these drifting shelves. Let us pause to consider the processes that create such archives. When two bodies collide, material scatters. Some escapes entirely, pushed into interstellar space. Some remains in orbit, slowly forming belts of rubble. Within these pieces, atoms are rearranged. Pressure can create new minerals. Heat can fuse grains together. Radiation over time alters isotopic ratios. All these changes are notes added to the record. None speak directly of intent, but all preserve evidence of events. For example, unusual amounts of certain metals have been found in meteorites. Scientists usually explain these as results of natural processes, perhaps the core of a parent body exposed after an impact. Yet if we imagine a larger frame, such findings could also resemble the scattered remains of something altered in less ordinary ways. Now we gently acknowledge what limits us. Most debris is never sampled. Of what does reach Earth, only a fraction is studied in detail. Even then, interpretations rely on models, not certainties. A single odd isotope ratio may have many explanations. A strange mineral pattern could come from chance, or from origins we cannot yet reconstruct. Absence of clear evidence is not evidence of absence. But presence of anomalies is not on its own evidence of design. We live in this balance, always weighing, never concluding too quickly. Let us linger briefly on the language of traces. Cosmic dust, collected in polar ice or high-altitude balloons, sometimes shows tiny grains with chemical enrichments not matching our solar system's average. Ancient sediments on Earth contain layers rich in iridium linked to impacts. In meteorites, we find grains older than the Sun, carrying isotopic fingerprints of distant stars. Each is a whisper, not a shout. Together, they create a murmur of history, textured but not clear. Now we may try a thought experiment. Imagine that long ago, an immense event took place in another star system. A structure or a body was shattered, scattering fragments into interstellar space. Step by step, some of these fragments drift outward, carried for millions of years. A fraction eventually crosses into our solar system. Some pass silently. Some, like Atlas, appear briefly and vanish. Others fall to Earth, becoming small meteorites, their origins masked by time. Centuries later, we analyze them, and we notice a slight anomaly in isotopes. It does not fit neatly into known models. We hesitate. We cannot say it is evidence of a war, only that it is unusual. And so the fragment becomes part of a silent archive, interpreted differently depending on the questions we bring to it. From here, we soften into a pause. The idea of invisible archives scattered through debris and dust is both humbling and uncertain. What we read as ordinary may carry extraordinary stories, or it may simply remind us of the galaxy's natural turbulence. We cannot resolve this fully. What we can do,
Continue to listen to the quiet language of matter, where absence and anomaly both become part of the record. In this way, even silence becomes an archive, reminding us that the cosmos preserves not only what is obvious, but also what is barely perceptible, waiting for us to notice with patience. What if every comet's orbit is not only a path through space, but also a sentence written in the quiet language of gravity? When we think of orbits, we often picture curved lines around stars, predictable and repeating. Yet the path of Atlas was not closed. It came from far beyond, traced a long arc through our solar system, and then left again, never to return. Its trajectory was like a phrase that begins but does not end, a fragment of speech carried on the wind. In this vast context, orbits become more than mechanics. They are records of past influences. Each deflection, each curve, reflects an earlier encounter. A comet is steered by gravity in the same way a leaf is guided by currents on a stream. The sun pulls, planets tug, passing stars shift directions. Over millions of years, the orbit reshapes. What we see at the moment of its arrival is only the final version of a long and quiet editing process. Let us pause with the mechanism. Gravity, though invisible, is simple at heart. It is the attraction between masses, pulling bodies toward one another. A comet passing near a planet can be bent, like a stone skipping off the edge of water. Sometimes it is captured into a bound orbit. Sometimes it is ejected entirely, cast into interstellar drift. For Atlas, its speed and angle meant it was not bound. It was what astronomers call a hyperbolic orbit, an open curve. This is why it will not return. It passed by the sun once, and now it is gone, following its line outward into the darkness. Now we must note our limits.
With such visitors, data are brief. They appear suddenly, remain visible for weeks or months, and then vanish. Their orbits can be calculated with some precision, but the history of how they arrived at those paths is hidden. Was Atlas scattered by a giant planet in another system? Was it once part of a larger body disrupted by an ancient collision? These questions remain open. Absence of clear markers does not close the possibility. What we hold is a snapshot, not the full film. The orbit itself, though, leaves subtle traces. Its openness tells us it is not native to our solar system. Its inclination, the tilt relative to our planetary plane, whispers of a different origin. The timing of its passage, arriving so soon after another interstellar visitor, Oumuamua, suggests either coincidence or perhaps that such visitors are more common than we thought. Each of these is part of the language of orbits, where geometry becomes archive and mathematics becomes memory. Let us imagine a small sequence. Suppose Atlas once orbited a star many light years away. Step 1. A distant stellar encounter perturbs its system. Step 2. Atlas is nudged onto a trajectory that leaves its star behind, beginning a journey across the interstellar medium. Step 3. After drifting for millions of years, it enters our solar system, curving briefly around the Sun before continuing outward. For us, it is a fleeting guest. For the cosmos, it is simply a line in a much larger pattern. This experiment shows us how orbits themselves can be storytellers. They preserve the memory of past forces, even when all else has been erased. We now soften toward a conclusion. The orbit of Atlas was open, fleeting, incomplete. It told us that it came from elsewhere and that it will not return. Whether it was only a fragile comet or a fragment of something more unusual, we cannot know. Yet in the gentle geometry of its path, we glimpse the quiet truth that every orbit is an archive. Some are cycles, repeating endlessly. Some are open arcs, fading into silence. Each is a sentence written in the gravity of time, leaving us only fragments to read before they drift away.
What if the way Atlas broke apart is not only a story of weakness, but also a record of forces it once carried within? When we watched it fragment into pieces, drifting softly away from one another, it looked fragile, almost inevitable. Yet fragmentation itself can be a language, a quiet testimony written not in words, but in the geometry of cracks. On Earth, when pottery breaks, the lines of fracture reveal where it was once stressed, where the material was weaker or already tired. In much the same way, a comet's disintegration reveals hints of its hidden structure and of the processes that shaped it. Let us place ourselves for a moment in the scale of such processes. A comet is not a single stone, but a cluster of dust and ice loosely bound. Its strength is low, like a snowbank in early spring, holding together but ready to collapse under warmth. As sunlight heats the surface, gases are released. They push gently but persistently. Sometimes these pressures are uneven, greater in one place than another. This imbalance creates stress, and eventually the body splits. To us, it seems sudden. To the comet, it is only the natural unfolding of forces long embedded within. Now we pause to note what we cannot see. For Atlas, the breakage was observed only from afar. No probes circled its fragments. We rely on changes in brightness, on faint smears of light captured by telescopes. From these, astronomers infer when the breakup began, how many pieces emerged, how fast they drifted. Yet the deeper details, the size of the fragments, the textures of their surfaces, the exact points of fracture, remain beyond us. Absence of this knowledge does not erase the event. It simply reminds us that our understanding is partial, always shaped by distance and by time. Still, fragmentation leaves indirect traces. The pattern of fading light showed that Atlas divided more than once, each stage scattering smaller and fainter debris. The fragments followed slightly different paths, like siblings leaving a home but staying near one another for a while. Some brightened briefly as fresh ice was exposed, then faded as it was consumed. In these patterns, scientists read the language of breakage, sudden exposure, short-lived activity, gradual silence. Each marker is a page in the comet's quiet archive.
Let us linger with a gentle thought experiment. Imagine Atlas as once part of a larger, more solid body. Step 1. A collision in deep space fractures it internally, but it stays together, held by weak gravity. Step 2. After millions of years of drifting, sunlight in our solar system awakens those hidden fractures, prying them open. Step 3. The body splits fully, scattering fragments along its orbit. Some disintegrate completely, turning to dust. Others survive longer, traveling outward. In this way, the pattern of breakage is both natural and layered, the final act of a process that began long before we ever saw it. We might also picture the fragments as quiet witnesses. Each carries within it a slightly different memory. One holds more volatile ice, another more dust, another scarred by a past shock. As they drift apart, they spread these different testimonies. Most are lost to our sight, too faint to track. But for a brief time, they allow us a glimpse of how one body contained many hidden stories. We may now soften into a conclusion. The fragmentation of Atlas can be explained by heat, by pressure, by fragility. Nothing requires more than this. Yet, in the way it broke, in the quiet scattering of its pieces, we are reminded that even disintegration carries meaning. The lines of fracture are a kind of writing. The dispersal of fragments is a kind of memory. Whether ordinary or extraordinary, the breakage left behind not emptiness, but traces, whispers in the dust that may travel onward long after the parent body has faded from view. In this perspective, fragmentation is not an ending. It is a transformation, a release of hidden patterns into the open before they dissolve once more into the silence of space.
What if the quiet embers of ancient fire are still drifting across the galaxy, and some of them reach us in the form of faint comets like Atlas? When we look into the night sky, we often see stability, stars shining calmly, planets moving slowly. Yet on larger scales, the universe has always been turbulent. Stars explode as supernova, releasing clouds of heavy elements. Black holes consume matter with unimaginable force. Collisions reshape systems, leaving trails of dust and gas behind. In this context, the idea of fire and ash is not only a metaphor, but also a way of describing the natural processes of creation and destruction. Atlas, fragile and short-lived, may be one small piece of such distant ash, a remnant of energies unleashed long before our time. To understand this, let us pause with the mechanics of cosmic fire. A supernova is the death of a massive star. In a single moment, it releases more energy than our sun will emit in its entire lifetime. This energy forges new elements, scattering them across space. Ash, in this sense, is not gray powder, but atoms and minerals, iron, carbon, oxygen, that later become parts of planets, oceans, and even living beings. When smaller bodies travel through regions shaped by these past fires, they may carry traces of them. Some fragments might show unusual isotopes, atoms of the same element with different weights, often formed under extreme conditions. If Atlas or any comet carries such patterns, it could be seen as a messenger from places marked by ancient fire. Yet we must be cautious. We cannot say with certainty where its materials came from. Our instruments catch only faint light, spectra blurred by distance and by its rapid disintegration. We can detect water, carbon compounds, some metals, but not the full history of their creation. Absence of detailed information does not prove that no unusual origin exists. It only tells us that the archive remains closed to us, at least for now. Still, indirect signs allow us to glimpse possibilities. The fragile structure of Atlas suggests it was old, altered by radiation over immense timescales. The brightness variations during its breakup hint at trapped volatiles, perhaps shaped in regions of high energy before being sealed within. Comparisons with other comets show both similarities and slight differences, enough to raise questions without resolving them. This is the language of ash, faint, incomplete, but persistent, reminding us of events that occurred long before our planet formed. Let us now allow ourselves a quiet thought experiment.
Imagine a distant system where two massive stars once lived side by side. Step 1. One star collapses, exploding as a supernova, scattering enriched material across surrounding space. Step 2. Fragments of dust and ice form from this mix, some incorporating the newly forged isotopes, some carrying scars of intense radiation. Step 3. One small body is nudged free, leaving its home system, drifting alone across the galaxy. After millions of years, it approaches our sun, warms, and begins to break apart. To us, it is simply a fragile comet, faint and fleeting. But in its dust lies the ash of an ancient star, fire transformed into silence, carried patiently through time. We can also picture another path, perhaps not a star's death, but a collision of two large bodies generated the heat, melting rock, scattering debris. Atlas, in this imagining, might be one splinter from that event. Again, we would not know. The traces are faint, and our tools are young. Yet the thought itself reminds us of scale, of continuity between violence and calm. Now we pause gently. Atlas may be only an ordinary comet, its fragility no more than the result of natural processes. Or it may carry within it atoms forged in violent fires long before our world existed. Both possibilities are humbling. What remains clear is that the cosmos is layered with memories, written not in words but in matter, drifting slowly through space. Each comet, each grain of dust can be read as ash from ancient fires, quiet reminders that creation and destruction are inseparable in the cosmos.
Long rhythm of the universe. In that rhythm, Atlas played only a brief note, fading quickly, yet leaving us with the thought that even in silence, the traces of fire endure. What if comets are not only visitors, but also messengers carrying quiet hints of stories too large for us to see whole? When Atlas arrived, it brought with it not only ice and dust, but also questions. Each fragment of matter it carried had traveled across immense distances, perhaps shaped by conditions we may never fully reconstruct. In this sense, a comet is less like a rock and more like a bottle cast into an ocean, drifting for ages until it washes ashore. Inside the bottle, there may be a message, though often written in a language we do not yet understand. To place ourselves in this context, let us imagine the scale. Our solar system is just one among billions. Between the stars lies the interstellar medium, a thin spread of dust and gas, sparse yet stretching endlessly. Within it, comets drift quietly, sometimes for millions of years. They gather no fuel, they have no engines. They simply follow the pull of gravity, the gentle push of passing stars, the quiet shaping of galactic tides. When one finally crosses into a planetary system, it is as if the messenger has found a shore. For us, it appears as a faint light against the sky, but the contents of its message are hidden in chemistry, in structure, in its fragile behavior near the warmth of a star. To understand how comets carry such information, we can rest a moment with their processes. A comet is a mixture of dust and volatile ices. Volatile means materials that evaporate easily, such as water, carbon dioxide, or methane. These ices lock away molecules formed in different places and times, like a freezer preserving old samples. As the comet warms, these trapped materials escape, forming tails of gas and dust. In those tails, we find not only beauty but also records. Spectral lines that tell us what chemicals are present, dust grains that later settle on Earth's surface, isotopes that hint at distant origins. Each part is a letter in the quiet message. Now let us pause gently with our limits. Atlas disintegrated quickly, leaving only a short window of study. The spectra were faint, the dust dispersed too fast to collect directly. We are left with incomplete notes. We do not know if Atlas carried unusual isotopes, or if its organics differed from ordinary comets. The absence of detailed samples is not proof that nothing remarkable was present. It only means the message may have arrived in a form we were not prepared to read. Still, even fragments of communication have meaning. The way Atlas brightened before breaking apart told us of its inner volatiles. The distribution of its fragments suggested an internal structure with weak points. Its orbit revealed its interstellar origin. These indirect signs become part of the comet's message. Like hearing only a few words of a sentence, we cannot grasp the full story, but we know that a story was there. Now we may allow ourselves a thought experiment. Imagine Atlas as a messenger carrying traces of a past event. Step 1. It drifts through a region shaped by stellar explosions, collecting atoms forged in those fires. Step 2. Its surface is scarred by cosmic rays during its long drift, altering some of its molecules into unusual forms. Step 3. It enters our solar system, begins to shed these molecules, and for a brief time they glow in sunlight, forming spectral lines for us to record. Later, some dust grains settle in Earth's upper atmosphere, where they may someday be studied. In this chain, the comet becomes a quiet letter, sent long ago, arriving almost by accident, carrying fragments of a history we can only piece together. We can also imagine another chain. Perhaps Atlas was not unusual at all. Its message may have been no different from countless other comets: water, carbon compounds, silicates. Yet even that ordinary record is important. It reminds us that the building blocks of planets and of life are widespread, drifting freely. In that way, the comet's message is not one of uniqueness, but of commonality, telling us
that the ingredients of worlds exist everywhere. Now we soften into a conclusion. Comets, as messengers, do not speak in clear voices. They whisper through dust, through spectra, through brief appearances that vanish too soon. Atlas may have carried something extraordinary, or it may have carried only what is ordinary and ancient. Either way, its role as a messenger remains. It reminds us that the cosmos is not silent. Its fragments travel, arrive, and dissolve, leaving behind hints that we may learn to read with patience. In this quiet rhythm, every comet becomes a message, even if most of the words are missing, and even if we must wait a long time before we can begin to understand what was written. What if fragility itself is not a flaw, but a way for a body like Atlas to release its hidden archive into space? When we saw it breaking apart, it seemed like an ending, but endings can also be transformations. A comet is not made to last forever. Its structure is loose, porous, easily undone by heat and radiation. In this sense, fragility is not failure, but a stage in a long journey, a way for materials to move from one form to another. To place ourselves in this view, let us imagine the scale of time. A comet can drift for millions of years in the cold, remaining almost unchanged. When it enters the warmth of a star's domain, the process of release begins. Gases escape, carrying dust with them. Cracks widen, pieces fall away. At first glance, it is loss, but if we think differently, it is also sharing. What was once hidden inside becomes scattered, carried outward into space, sometimes even reaching planets. In this way, fragility is less about collapse and more about transition. Now let us pause with the processes themselves. The ice inside a comet sublimates, changing directly from solid to gas. This creates pressure in pockets. If the outer shell is weak, it bursts, releasing jets of gas and dust. Each jet carries material that was preserved since the comet's birth. When Atlas disintegrated, it exposed inner layers we otherwise could never have seen. For a short time, its fragility made its memory visible. We must also note our limits. With Atlas, we did not collect samples. We saw only its light, fading quickly, its fragments dissolving into the background. We cannot tell how much of its dust reached Earth, nor what exact molecules it carried. Absence of direct measurement is not absence of significance. It only means we read the event indirectly, through brightness patterns, through changing shapes, through quiet traces left in instruments tuned to the sky. Fragility writes its own language of signs. The sudden dimming of Atlas marked its disintegration. The uneven spread of fragments suggested weak zones in its structure. The color of its coma hinted at organic compounds, fragile molecules that survived until the very end. These signals are not loud. They are soft imprints, like footprints in snow. They fade quickly, but they tell us something about the path that was taken. Now we may try a small thought experiment. Imagine Atlas drifting through interstellar space for countless ages. Step 1. Radiation slowly weakens its bonds, leaving it brittle. Step 2. It enters our solar system, where sunlight awakens trapped gases. Step 3. It breaks apart, scattering dust into the solar wind. Some grains may wander for centuries, perhaps drawn into Earth's atmosphere, settling in polar ice or deep-sea sediments. One day, long after its name is forgotten, a scientist may find a grain, analyze its isotopes, and notice something slightly unusual. The message of Atlas would then have reached us, carried through fragility. We could imagine another sequence as well. Perhaps its fragments never reach Earth, but instead drift outward again, becoming part of interplanetary dust. Over time, they may join other streams, contributing quietly to the glow of zodiacal light we see in our skies before dawn. In that case, fragility transforms Atlas from a single body into part of a diffuse, gentle band of light that surrounds us all. From here, we soften toward a pause.
Fragility, often seen as weakness, can also be continuity. A comet that endures without breaking keeps its archive locked away. A comet that fragments allows its archive to spread, though at the cost of its own form. Atlas chose, or rather was forced into, the latter path. Whether it carried extraordinary secrets or only the ordinary dust of the galaxy, we cannot know. But its fragility reminds us that survival and loss are not opposites. They are stages in the same rhythm, one leading into the other, both leaving traces in the silence of space. What if this silence left behind by Atlas is not emptiness, but a quiet reminder that absence can also be part of the record? When we think of knowledge, we imagine evidence, samples, photographs, numbers written in tables. Yet the cosmos often offers us gaps instead. A comet disintegrates too quickly, leaving no fragment to collect. A signal fades before instruments can measure it. A trace hides beneath layers of dust, waiting for centuries to be uncovered. In these gaps we do not find certainty, but uncertainty itself can teach us. It slows us, asking us to remain patient. To understand this more deeply, let us place ourselves in the scale of astronomical observation. Telescopes can see faint light, but only while an object is still there. Once Atlas broke apart, it became almost invisible. No fragments large enough to follow remained. Scientists recorded what they could: the brightening before the split, the dimming afterward, the fading trail. What is missing is as notable as what was captured. The archive is incomplete, a book with missing pages. But even missing pages tell us something, that there was more to the story than what we hold in our hands. Now we pause with the processes of absence. In science, when a result is not found, it is called a null result. It does not mean nothing exists, it means nothing was detected within the limits of the tools. A comet that dissolves before collection leaves behind a null result. This does not prove that it carried nothing unusual, it only proves that its traces were too faint, too brief, too scattered for us to see. Absence of proof, as we remind ourselves, is never the same as proof of absence. The cosmos remains larger than our reach. Still, absence itself can be read as a kind of language. The rapid disappearance of Atlas suggests extreme fragility. The lack of surviving fragments hints at how loosely bound it was. The silence in the data becomes a marker of its structure. Even the dust too fine to track may eventually settle in Earth's layers, leaving faint enrichments that could be studied in the distant future. In this way, absence becomes presence in another form, just delayed. Now let us try a gentle thought experiment. Imagine Atlas scattering into dust too fine to see. Step 1. Solar wind carries these grains outward, dispersing them through the solar system. Step 2. Some grains drift across Earth's path, settling in the upper atmosphere, descending slowly over decades into snow or sea. Step 3.
Centuries later, scientists study ice cores or sediments and notice a faint layer rich in certain organics, not matching known local sources. They cannot link it directly to Atlas, but it becomes part of a wider puzzle. The comet's absence at one scale transforms into presence at another. We can imagine another sequence as well. Perhaps no grain from Atlas ever reaches Earth. Perhaps all disperse into interplanetary dust, blending into the diffused glow of zodiacal light we see at dawn. In that case, its absence from our records becomes its contribution to a soft background, a reminder that even lost objects still influence the quiet brightness of the sky. From here we move toward a pause. Atlas left no solid evidence behind, only a short record of light and disappearance. Yet in that very absence lies its message. It reminds us of the limits of knowledge, of the importance of patience, of the humility required to read silence as carefully as we read data. Absence does not mean nothing. It means that part of the archive remains hidden, waiting in forms we may not yet recognize. In the
rhythm of cosmic time, even silence has meaning, and even what vanishes leaves traces for those who are willing to listen gently. What if the meaning of visitors like Atlas can only be found not in a single object, but in patterns spread across many arrivals? A lone comet may look fragile, ordinary, unremarkable, but when we step back and view several, when we compare their behaviors, their chemistries, their trajectories, we begin to notice rhythms. In astronomy, this is the power of statistics. One comet can only whisper. A group of them begins to form a chorus, even if faint. To place ourselves in this wider scale, let us think of time as a long ledger. Across billions of years, countless comets have crossed into planetary systems. Most were never seen. Only recently have we begun to record them with precision. The two interstellar visitors we have noticed so far, Oumuamua and Atlas, are not enough for conclusions. They are like two letters found without a full alphabet. Yet even with so little, we begin to wonder whether such visitors are more common than we thought. The statistics are not yet clear, but the possibility lingers. Now let us rest for a moment with the mechanisms of statistical reading. Patterns emerge not by studying one case in isolation, but by looking at many and asking what repeats. If most comets from outside our system show extreme fragility, this could suggest that the interstellar environment naturally produces weak bodies. If instead they arrive varied, some strong, some weak, then each case may tell us a different origin story. In this way, the statistics become not only numbers, but a method of listening. The cosmos rarely explains itself directly. It speaks in distributions, in likelihoods, in small biases that build significance when gathered together. Yet here we pause with humility. Our sample is tiny. 2 visitors are not enough. Even dozens would only begin to outline a pattern. The gaps remain immense. Absence of repeated examples does not mean they will not appear. And even when they do, distinguishing between natural and extraordinary origins will remain delicate. A cluster of fragile bodies could point to natural processes alone. It could also, though less likely, hint at past events of another kind. We cannot yet know. Still, the language of statistics already leaves traces. The timing of discoveries shows us that with new instruments, interstellar visitors are being noticed more frequently. The brightness curves of Atlas and its quick fading may later be compared to future arrivals, becoming part of a data set larger than itself. In this way, a single fragile comet transforms into a data point, modest yet meaningful, contributing to an archive that will outlive it. Let us now imagine a thought experiment, stretched gently in 3 steps. First, suppose we observe 10 interstellar comets over the next century. Each breaks apart quickly near the Sun. The pattern becomes clear. Fragility is their shared trait. Second, we ask why. Perhaps radiation in deep space weakens them over long drifts, or perhaps they were born in environments unlike our own. Third, centuries later, hundreds of visitors have been logged, and their statistics reveal something unexpected. A slight enrichment in metals across many, unusual compared to solar system comets.
The pattern itself becomes a whisper of history, too faint in one case, but audible in the some. Or we may imagine a quieter sequence. Perhaps interstellar comets arrive with no consistent difference from our own. Some fragile, some sturdy, some ordinary in chemistry. In this scenario, the statistics tell us not of difference, but of similarity, reminding us that the building blocks of matter are shared widely across the galaxy. Either way, the archive is valuable. We now soften into a pause. Statistics do not provide certainty. They provide tendencies, rhythms, suggestions. Atlas alone cannot tell us if it was extraordinary, but in combination with others, it may one day reveal whether its fragility was common or rare.
Whether its chemistry was ordinary or unusual. The silence of small numbers will eventually give way to patterns, and in those patterns we may hear the echoes of processes far older than our planet. Until then, we remain patient, listening not for single voices, but for the gradual harmony of many arrivals. What if the faint fingerprints of long-vanished fires are still carried within the atoms of fragments like Atlas? When we look at comets, we see ice, dust, and organic molecules. Yet hidden among them are isotopes, atoms of the same element with slightly different weights. On Earth, we measure isotopes and raindrops to learn about climate, in rocks to study the age of mountains, in sediments to trace past oceans. In space, isotopes become something more, quiet witnesses of ancient furnaces, of stars that exploded long before our sun was born. To place ourselves gently in this scale, let us imagine time as a deep archive. Billions of years ago, massive stars lived briefly and died in supernovae, scattering elements across the galaxy. Some of those elements drifted, settled into clouds, and later became part of new systems. Every comet we see may carry within it isotopic signatures of those earlier events, like faint handwriting in the margins of a book. Atlas, though fragile and brief, might also have contained such quiet handwriting, though it slipped from our hands before we could read it closely. Now let us pause with the processes. Isotopes form in stellar cores and in explosions. For example, carbon has stable forms, carbon-12 and carbon-13. Their ratios vary depending on where they were born. Oxygen has oxygen-16, oxygen-17, oxygen-18, each forged in slightly different conditions. By measuring these ratios, scientists trace origins, much like a chemist can trace the source of water by its mineral content. In comets, isotope ratios can show whether their material formed in the cold outer regions of a system or nearer to stars. They may even show exposure to cosmic rays, which alter atoms over millions of years. But here we must pause again. With Atlas, such measurements were never possible. It disintegrated too quickly, its fragments too faint. We do not know what isotopic story it carried. Absence of evidence does not mean the absence of an unusual origin. It means only that the archive was closed before we could open it. Still, the language of isotopes surrounds us in indirect ways. In meteorites, we find tiny grains older than our solar system, carrying exotic isotopic ratios that can only come from distant supernovae. In comet dust collected by spacecraft, unusual enrichments in deuterium, the heavy form of hydrogen, have been observed. These enrichments suggest formation in extremely cold environments. By extension, Atlas II may have carried ratios outside our local norms, silent signals of where it drifted and what it endured. Now let us imagine a quiet thought experiment. Step 1. A fragment like Atlas forms in a distant system, its ice locking in a high ratio of deuterium, far higher than Earth's water. Step 2. After drifting for millions of years, it enters our solar system, releases dust and vapor. Step 3. Centuries later, traces of that dust found in ice cores show isotopic enrichments, puzzling researchers who compare them with other records. They cannot prove origin, but the pattern hints at a history longer than Earth. Or imagine another chain. Atlas once carried grains altered by intense cosmic rays, isotopes reshaped by energies stronger than those near our sun.
In drifting into our skies, it shed this dust invisibly. Most was lost, but perhaps a few grains entered Earth's atmosphere, unnoticed. They now lie in sediments waiting for someone to stumble upon them, to measure ratios that do not quite match familiar sources. These are only possibilities, but they remind us of the scale of memory stored in atoms. From here, we soften toward a pause. The isotopic echoes of Atlas remain unknown. Perhaps it was ordinary, its ratios matching other comets. Perhaps it carried
unusual enrichments, a silent archive of places we will never see. Either way, the thought of isotopes as messengers is humbling. They are fragments of ancient fire, carried patiently across time, surviving through transformations that erased almost everything else. Atlas is gone, but the idea remains. Every comet, even the most fragile, may be a library written not in words, but in the delicate balance of atoms, waiting for us to learn how to listen more carefully. What if the faint glow of Atlas in the infrared was not only a trace of heat, but also a gentle memory of energies it once endured? When astronomers looked at it, they measured light not only in the visible spectrum, but also in the longer wavelengths of infrared, where heat is revealed. A comet's faint warmth is like a whisper, almost invisible to our eyes, yet detectable by instruments. It tells us how dust absorbs sunlight, how it re-radiates energy back into space, and how the structure of the body shapes this balance. In this quiet language, a comet's thermal signature becomes more than a number. It becomes a shadow of its past. To place ourselves in this frame, let us think of scales of temperature. In everyday life, we feel warmth when sunlight touches our skin or when a stone holds heat after a summer day. In space, where air does not carry heat, bodies absorb light directly and then release it slowly. Dark surfaces absorb more, bright surfaces reflect more. A comet like Atlas, covered in dark dust, would have absorbed sunlight and radiated it back in the infrared. The pattern of this emission is a kind of fingerprint, revealing grain size, composition, and surface texture. For Atlas, the signals were faint, blurred by its quick disintegration. Yet even in their faintness, they hinted at fragile dust scattering warmth unevenly. Now we pause to notice our limits. Infrared data on Atlas were scarce, its brightness too low, its fragments too diffuse. We do not know whether its emission held anomalies or whether it was entirely ordinary. Absence of strong evidence does not confirm emptiness. It only reflects the challenge of measuring something so fragile. Our view remains incomplete, and in that incompleteness lies both humility and patience. Still, the language of infrared has meaning beyond Atlas itself. In other comets, variations in thermal emission reveal coatings of organic compounds or surfaces altered by heating. Sometimes unexpected glows appear, hinting at grains larger or denser than expected. Such data remind us that heat carries history. A faded ember tells us of a fire long past. A warm stone tells us of the sun that once touched it. In the same way, an interstellar comet's warmth, however faint, carries echoes of its long journey. Let us rest with a thought experiment. Step 1. Imagine Atlas drifting in deep space, exposed for millions of years to faint starlight and cosmic rays. Its outer layers darken, its dust becomes brittle. Step 2. As it enters our solar system, sunlight strikes it with new intensity, heating its surface unevenly. Cracks widen, dust glows faintly in the infrared, each grain re-radiating the energy it receives. Step 3. Telescopes record this glow for only a short time, before the comet fragments and fades. The thermal signature becomes not a steady archive, but a brief trace, like a shadow cast and then dissolved. Or picture another path. Perhaps Atlas once endured more sudden heating by passing close to another star, or by an earlier disruption. Its materials could have carried scars, altered structures that glowed differently in infrared. We cannot know if this was so, but the thought itself helps us appreciate how faint warmth may act as a quiet archive of past encounters.
From here, we soften into a pause. The shadows of Atlas in infrared do not reveal a dramatic story. They leave us only with faint hints of dust releasing warmth into space. Yet even these whispers remind us that every body carries a thermal memory. Heat is absorbed, transformed, released, and measured, becoming part of the cosmic archive. Whether ordinary or unusual, the faint glow of Atlas was
still a testimony, a reminder that even what seems most fragile can shine with the memory of light it once received. In that glow, however brief, we glimpse the continuity of energy and matter across time, written not in words, but in the quiet language of warmth fading back into darkness. What if the dark and scarred surfaces of comets are not just the result of ordinary heating, but also quiet memories of forces more intense than we usually imagine? When we observe such bodies through telescopes, we often see them as blackened, with albedo, reflectivity, so low they resemble lumps of coal. Yet sometimes, patches glimmer slightly brighter, as though scraped clean or burned differently. On Earth, a stone, polished by water, tells of the stream that shaped it, and a scorched wood beam preserves the memory of fire. In the same way, a comet's surface carries quiet marks of what it has endured. To place ourselves gently into this scale, let us think of time not in years, but in cycles of orbits and passages. A comet spends most of its life far from heat, in cold storage, coated by layers of dark dust. When it approaches a star, volatile gases awaken and jets erupt, peeling away parts of the crust. The outer surface becomes irregular, some areas blackened, some freshly exposed. The scars remain as long as the comet survives. Atlas, fragile and short-lived, showed us very little detail before breaking apart. But even its rapid disintegration suggested that its surface was weakened, layered, perhaps already fractured before its arrival. Now we pause to reflect on the processes that may leave such scars. Radiation darkens surfaces slowly, creating carbon-rich layers. Impacts with tiny grains chip away material. Sudden heating can crack the crust or leave glassy coatings. These scars are cumulative, shaped over millions of years. They are not loud signs, they are quiet textures, like lines on an aged face. Scientists read them indirectly, through brightness curves, through spectra, through comparisons with other comets observed more closely. Yet here we must acknowledge the limits. Atlas was too faint, too fleeting. No spacecraft mapped its terrain, no close images were captured. What we imagine of its scars is based on analogies to other comets, like 67P visited by Rosetta, which showed pits, fractures, cliffs, and surfaces both bright and dark. Atlas may have carried similar marks, or perhaps even stranger ones. Absence of images is not absence of features, it is only the silence of distance. Still, scars have a language of their own. A dark surface tells us of long radiation exposure. A brighter patch suggests fresher material exposed by a break. Variations in reflectivity can reveal compositional differences, ice in one place, organics in another. In rare cases, melted textures hint at more sudden heating, though whether by natural flares, collisions, or something else, we cannot easily say. These are quiet archives, written not in layers we can cut through, but in surfaces we can glimpse before they vanish. Now let us try a thought experiment. Step 1. Imagine Atlas once passed close to a star before arriving here, its surface partly melted, creating a glassy patch among otherwise dark dust. Step 2. Over millions of years, radiation roughened this patch, but it remained slightly brighter than its surroundings. Step 3. When Atlas entered our solar system, this scarred surface briefly reflected sunlight, a glimmer recorded faintly in telescopes. Later, as the comet broke apart, the scar vanished into dust, but the record of brightness remained in archive data. Or we may imagine another chain. Atlas formed with internal fractures. When jets of gas erupted, they burst through weak spots, leaving fresh craters or pits on its surface. These scars may have weakened it further, accelerating its breakup. In this imagining, the comet's surface was not just passive covering, but an active participant in its disintegration, bearing the story of stresses long hidden within. From here, we soften toward a pause. Scars on comets are inevitable. They may be ordinary, formed by
radiation and heat. Or they may carry hints of encounters beyond our solar system, shaped in environments we can only imagine. With Atlas, we cannot know. Its surface dissolved too quickly for us to read. Yet even in absence, we are reminded that surfaces are memory. Each scar is a record, each patch a quiet sentence in a story far longer than our observations. Whether natural or unusual, the darkened face of a comet teaches us humility, that even the most fragile bodies can carry scars across millions of years, only to reveal them briefly before fading into silence once more. What if the fragments of Atlas that scattered into space were not only remnants of a broken body, but also quiet testimonies of what once held together? When we saw the comet dissolve into pieces, it may have seemed like an end. Yet every fragment continued its own small orbit, carrying within it the same material, the same history, the same traces of processes that shaped the parent. In this sense, fragmentation is not silence, but multiplication of voices, each piece whispering part of the same long story. To place ourselves in this picture, let us think of fragments as witnesses. On Earth, when a vessel breaks, each shard of glass reflects part of the original shape. No fragment alone contains the whole, but together they preserve memory of what was lost. With comets, fragments behave in a similar way. Their paths diverge gently, yet they remain close for a time, forming clusters of faint lights. Some brighten briefly as fresh ice is exposed. Others fade quickly into dust. Each one testifies differently. Scientists trace their brightness curves, their separations, their survival times, and in those patterns they read the quiet archive of stresses hidden inside the original. Now we pause to notice the processes that create such testimony. A comet is loosely bound. When heat or pressure exceeds its fragile cohesion, cracks spread and the body divides. Each new fragment is itself weak, prone to further splitting. This cascade can continue until only dust remains. But in the short period between breakage and dissolution, fragments allow us to glimpse hidden layers. By comparing how each behaves, scientists infer differences in composition, density, and structure. In this way, fragmentation becomes less a loss and more a brief window of revelation. Yet here we must rest with uncertainty. Atlas was visible only for a short time. Its fragments were too faint to follow long. We do not know how many survived, nor what exact compositions they carried. No probe collected their dust. Absence of this data does not mean the fragments were meaningless. It means simply that the testimonies were given in voices too quiet for us to hear clearly. Even so, the language of fragments leaves indirect traces. The rapid fading told us they were small, fragile. The uneven brightening suggested differences in volatile content, some releasing gas quickly, others holding back. The pattern of separation hinted at how the parent body fractured, perhaps along pre-existing lines of weakness. These are markers, subtle yet lasting, preserved in observational records. Now let us try a thought experiment. Step 1. Imagine Atlas breaking into 10 fragments, each carrying different amounts of trapped gas. Step 2. As they drift outward, some brighten in sudden bursts, others fade almost immediately. Step 3. Their dust spreads, entering the solar wind, carried across the system. Centuries later, tiny grains from these fragments may settle into Earth's sediments. A geologist studying them might notice unusual organics not easily traced to known sources. The fragment's testimony, once lost in the sky, would continue in layers of stone. Or let us imagine another sequence. Perhaps none of the fragments survive long. Instead, they dissolve entirely into dust. Over years, this dust blends into the broader interplanetary cloud, adding to the faint glow of zodiacal light. In this case, the fragment's testimony is not individual but collective, absorbed into a quiet background that envelops us each dawn and dusk. Their message is not in detail but in presence, reminding us of how fragile matter persists by dispersing. From here, we soften toward a pause. The fragments of Atlas, though faint and quickly lost, remind us that every division carries meaning. Each piece is a witness, carrying traces of the same origin. Whether studied individually or dissolved into background dust, they remain part of the long archive of space. We cannot know their full story, but we can rest with the thought that in breaking, Atlas did not vanish. It multiplied its voices, scattering quiet testimonies across the sky, leaving us with a reminder that even in disintegration, memory continues in new and gentler forms. What if the dust released by Atlas was not simply debris, but a trail of memory stretched across the solar system? When a comet breaks apart, the fragments are carried away by sunlight and solar wind, spreading gradually into long streams. To our eyes, these streams are faint, almost invisible, yet they linger for years, sometimes for centuries. In this sense, the dust is not absence, but continuity. It preserves the comet's path long after the body itself has vanished, like a thin mist marking where something once passed. Now let us gently place ourselves in the scale of this process. Dust grains from comets are incredibly small, often no wider than a hair, yet countless in number. Once released, they follow orbits close to the parent body's track. Over time, these grains can intersect Earth's orbit, entering the atmosphere as meteors. Most burn up quietly, no larger than sparks. A few survive as microscopic particles, drifting down into oceans, into ice, into soil. Each grain carries the chemistry of its origin, preserved like a sealed letter. In this way, the comet's dust becomes part of Earth, layered into archives we may study much later. Now we pause with the mechanisms themselves. Solar radiation exerts pressure on dust grains. The smaller the grain, the more strongly it is pushed. This causes the particles to spread into wide tails or into bands along the comet's orbit. The solar wind, a flow of charged particles from the sun, also carries them. Over years, the dust disperses further, creating broad streams of material that may circle the sun like invisible ribbons. With Atlas, its sudden disintegration meant a vast release of dust in a short time, forming a trail far larger than usual. Yet because it faded quickly, the trail was faint, and only parts of it were observed. Here we must acknowledge our limits. No spacecraft flew through Atlas's dust, no samples were collected directly. We rely on models, on telescopic images, and on parallels with other comets. We cannot know exactly how much dust was released, nor its precise composition. The absence of detailed evidence does not mean the trail was empty. It means only that it remains hidden, waiting perhaps for indirect discovery in sediments or future measurements. Still, the dust leaves quiet signs. Meteor showers on Earth are one such language. When our planet crosses a comet's trail, we see streaks of light in the night sky. Some are predictable, tied to well-known comets. Others appear unexpectedly, from trails left by forgotten or faint visitors. Perhaps one day, dust from Atlas will join this cycle, creating a small, unnoticed shower, a brief sparkle across the sky. The trail itself is an archive, though one written in drifting particles rather than in stone. Let us now imagine a thought experiment. Step 1. Atlas breaks apart, scattering billions of grains. Step 2. These grains form a diffuse stream, circling the sun, slowly shifting under the pull of planets. Step 3. Centuries later, Earth crosses the stream. Most grains burn up unseen, but a few settle gently on polar ice. Thousands of years later, scientists drilling deep into glaciers find a thin layer enriched with exotic organics, grains of interstellar dust older than Earth. They trace its age and find it matches the time when Atlas disintegrated. The comet's dust, once invisible, has become a marker in Earth's geological archive. Or we may imagine another path. Perhaps Atlas's dust never crosses Earth. Instead, it disperses into the zodiacal cloud, the faint band of light we see along the ecliptic at dawn or dusk. In this way, the dust becomes part of a larger glow, no longer distinguishable as its own, yet still present. Its archive is not in specific grains, but in the soft brightness of the sky, a shared memory folded into a collective background. From here, we soften into a pause. Dust may seem fragile, trivial, almost nothing. Yet in astronomy, dust is a carrier of history. It records chemistry, it marks paths, it settles into layers that last long after comets dissolve. Atlas is gone, but its dust continues, drifting silently, joining larger streams, perhaps leaving faint signals for us to find. In this way, even the smallest grains become archives, quiet testimonies that matter. Once set in motion, does not end but transforms into new forms of memory scattered across the cosmos. What if the faint organics once carried by Atlas were not simply ordinary molecules, but fragments of chemistry that began in environments far beyond our solar system? When scientists study comets, they often find compounds containing carbon, hydrogen, oxygen, and nitrogen. These are not life themselves, but they are the building blocks of life. On Earth, such molecules can be compared to flour, water, and salt before bread is baked. They are ingredients, not the final form. Comets preserve these ingredients for billions of years, keeping them frozen until they are released again by sunlight. To place ourselves in this frame, we should think of scale. Organic molecules form in cold clouds of gas and dust between stars. Radiation sparks reactions, simple atoms linking into more complex chains. Over time, these chains are trapped in ice on grains of dust. Later, when these grains gather into comets, the molecules are sealed inside, preserved like recipes written long ago and kept unopened. When a comet approaches a star, these archives thaw. For a brief time, they become visible in the comet's tail as gases and dust scatter into space. In Atlas, this process must have occurred, though too briefly for us to record in detail. Now we pause with the mechanisms of detection. When light from the sun passes through gases around a comet, certain wavelengths are absorbed. These create patterns called spectral lines. Scientists can read them as signatures of particular molecules: water, carbon monoxide, methane, even complex organics. In missions like Rosetta, probes measured dozens of such compounds in a single comet, some surprising in their variety. Atlas, fragile and fleeting, left us only partial notes. Its light was faint, its disintegration too rapid. We cannot know whether it carried unusual molecules or only the expected ones. Absence of detailed data does not mean absence of richness. It means only that the record escaped us this time. Still, the language of organics remains clear in the broader archive. Comets studied before have shown amino acids, alcohols, simple sugars, molecules that on Earth are linked to life. They do not prove life elsewhere, but they prove that life's ingredients are widespread. Atlas, whether ordinary or not, likely carried similar material, drifting quietly across the galaxy until its fragile structure surrendered. These are not loud declarations, but quiet continuities. Now let us imagine a thought experiment. Step 1. Suppose Atlas carried a set of organics slightly different from most solar system comets, perhaps enriched in unusual ratios shaped by cosmic radiation. Step 2. As it disintegrated, dust carrying these molecules scattered. A fraction may have drifted into Earth's atmosphere, falling gently over years as micrometeorites. Step 3. Centuries later, a scientist analyzing ice cores finds an anomaly: organic molecules with isotopic patterns not matching local sources. The trace is faint, unprovable, but it adds a question to the archive. Atlas's chemistry thus continue its quiet testimony long after its light was gone. Or let us picture another path. Perhaps Atlas was entirely ordinary, its organics matching countless other comets. In that case, its testimony is still meaningful. It would remind us that even across interstellar distances, the same chemistry recurs, stable and patient. The galaxy itself seems to write similar recipes again and again, whether in our system or far away. This repetition is as humbling as any anomaly. From here, we soften toward a pause. The organics of Atlas remain unknown to us, hidden by its swift dissolution. Perhaps they were extraordinary, perhaps entirely common. Either way, they remind us of continuity. Simple molecules, fragile but persistent, drift through space, carried in ice and dust for billions of years. They do not shout their message, they whisper, patiently, across epochs. Atlas was one such whisper, now dissolved, but its possibility remains folded into the larger archive of the cosmos. A reminder that even silence may carry the memory of chemistry written long before us. What if the faint gases released by Atlas were not only the breath of a dissolving comet, but also quiet signals of environments long forgotten? When a comet warms, its ices turn directly into vapor, a process called sublimation. The gases escape, forming a glowing coma and a tail. To our eyes, this looks like a mist trailing across the sky. But within that mist lies chemistry preserved for billions of years. Each molecule is a note from the past, telling of the temperature and radiation under which it first formed. To place ourselves in this context, let us think of gases as voices. On Earth, air carries smells from places we cannot see. A hint of smoke reveals a distant fire. The salt in a breeze reveals the sea. In space, gases escaping from comets are similar. They reveal the hidden interior, speaking briefly before fading into the solar wind. In Atlas, those voices were faint and fleeting, but still measurable. Water vapor dominated, as in most comets, yet there were also hints of carbon-based gases, fragments of ancient chemistry. The balance of these components may have held clues to its origin, though we could not hear them clearly before it disintegrated. Now we pause to rest with the mechanisms of reading these voices. When sunlight passes through gas, certain wavelengths are absorbed, leaving patterns in the spectrum. These patterns act like barcodes, each molecule leaving its unique set of lines. Astronomers can read them to identify water, carbon monoxide, carbon dioxide, ammonia, and more complex organics. With strong comets, dozens of gases can be cataloged. With Atlas, the faintness of its coma limited us to a few, and the rest remain uncertain. Absence of clear detection does not mean absence of presence. It means only that the whisper was too quiet for our instruments at that time. Still, the language of gases leaves indirect traces. The way brightness increased before its break suggested that buried pockets of volatile ices were released suddenly. The short bursts of activity implied uneven distribution, perhaps layers laid down in different environments. Even the rapid fading afterward told us something, that the reserves of volatile material were not deep. These quiet patterns form part of Atlas's archive, even if the details are incomplete. Now let us imagine a gentle thought experiment. Step 1. Suppose Atlas carried unusual ratios of gases, perhaps more carbon monoxide than expected, hinting at colder origins far from any star. Step 2. As it approached our Sun, these gases escaped quickly, recorded faintly in telescopes. Step 3. Though no spacecraft collected them, traces might still linger in upper layers of Earth's atmosphere, falling with cometary dust, perhaps to be found one day in subtle enrichments in trapped air bubbles within ancient ice. In this way, the gas would leave a delayed message, unnoticed in its time, but discoverable in the future. Or let us imagine another chain. Atlas was entirely ordinary in its gases, showing
The usual balance of water and carbon dioxide. In this case, its message would still be meaningful. It would tell us that interstellar visitors carry the same chemistry as local comets, reinforcing the idea that the building blocks of matter are common throughout the galaxy. Ordinary does not mean unimportant. It means connected, continuous. From here, we soften into a pause. The gases of Atlas were faint, quickly lost in the solar wind. We may never know their full balance. Yet even in absence, the thought remains. Every comet breathes out an archive, each molecule a letter from the past. Some messages we catch, others drift away unnoticed. Atlas has left us with both, a handful of faint signals and a larger silence. Together they remind us that knowledge often comes not from complete voices, but from fragments, whispers that ask us to listen with patience, knowing that even absence may carry meaning in the quiet archives of the cosmos. What if the faint light of Atlas was not only a reflection of sunlight, but also a quiet code, a sequence of patterns holding more than brightness alone? When astronomers observe a comet, they do not see its solid body directly. What is visible is the light scattered by dust, the glow of gases excited by radiation, the subtle flickers caused by fragments shifting in and out of view. This flickering is not noise. It is a form of language, though one we can only read partially.
Each rise and fall in brightness marks a process inside the comet, like breathing rhythms in a sleeping body. To place ourselves in this view, let us think of light as a diary. On Earth, we learn about weather by watching clouds change shade in the sky. In space, we learn about comets by watching how their light changes over days and weeks. A sudden brightening may mean gas erupting from beneath the surface. A dimming may show that fragments have drifted apart. Repeating cycles may hint at rotation, as different sides turn toward us. Atlas, before it broke apart, showed such changes. Its light grew steadily stronger as it approached the sun, then unexpectedly surged, then weakened as it began to fragment. These variations were its diary entries, brief and incomplete, yet meaningful. Now let us pause with the mechanisms of brightness. A comet shines in two ways: by reflecting sunlight from dust, and by emitting light from gases energized by the sun. Dust reflects like powder on a tabletop. Gases emit specific colors: green from diatomic carbon, blue from ionized carbon monoxide. Together, they create the soft glow we call a coma. As the comet breaks apart, more dust may scatter light, causing a surge. As dust disperses, brightness fades. This interplay is subtle, and its patterns are what astronomers read. Yet we must acknowledge the limits. With Atlas, the data came mostly from ground-based telescopes. Its faintness, combined with its rapid decline, meant that the light curve, the record of brightness over time, was incomplete. We do not know exactly how quickly the surges occurred, nor whether smaller fragments carried on glowing unnoticed. Absence of such detail does not mean the diary was empty. It means only that our reading was too rushed, too distant, leaving gaps between the lines. Still, the language of light leaves indirect traces. The timing of Atlas's final surge suggested a catastrophic release of trapped volatiles. The asymmetry of its fading implied fragments scattering unevenly. Even the exact shape of its tail, slightly curved, carried information about the balance between solar pressure and particle size. These are quiet markers, subtle entries in its luminous record. Now let us try a gentle thought experiment. Step 1. Imagine Atlas as it neared the sun, heating unevenly. One pocket of ice releases gas in a sudden burst. The comet brightens sharply, its glow recorded by telescopes as a spike. Step 2. Fragments drift away, reflecting less sunlight, causing brightness to waver, as though the diary page were torn mid-sentence. Step 3. As the dust disperses, the light fades, leaving only the recorded curve in archives. Centuries later, astronomers comparing many such curves see a pattern: that interstellar comets often show sudden surges before vanishing. The faint diary of Atlas would then become part of a larger memory. Or let us imagine a quieter sequence. Perhaps its brightness behaved no differently from solar system comets, showing ordinary surges and fades. In that case, its diary is still valuable. It shows us that interstellar travelers share the same rhythms, governed by the same sunlight, the same fragile chemistry. The familiarity itself is testimony that the language of light is universal, not bound to one system. From here, we soften into a pause. The brightness of Atlas was fleeting, a glow that rose, flickered, and dissolved. It did not leave solid fragments for us to study, but it left a light curve, an archive of faint signals preserved in digital records. These signals may be ordinary, or may hold hidden patterns yet to be noticed. Either way, they remind us that light itself is memory. Every flicker is a trace, every fade is an entry, every surge a brief word in a diary, written not in ink, but in brightness carried across the dark. What if the trajectory of Atlas was not just a path through our skies, but also a trace of a much longer journey, stretching back into the unknown reaches of the galaxy? When we observe a comet's orbit, we see more than its present movement. We glimpse the story of how gravity has guided it, shaped it, and finally delivered it into view. Each curve, each deflection, each speed tells us about encounters it may have had, forces that once nudged it, perhaps even systems it once called home. To place ourselves in this perspective, let us think of an orbit as a line written across a vast page. In the solar system, planets draw near circles, steady and predictable. But interstellar visitors carve hyperbolas, open paths that do not close, lines that enter and exit, never to return. Atlas carried such a trajectory, hinting that it came from far away, that its path had no beginning here and no end here, only a brief crossing. Like a bird flying across a field, leaving only a shadow in its passage, the orbit of Atlas was its fleeting mark upon our sky. Now we pause gently with the mechanisms behind this tracing. Gravity pulls on every object. A comet passing near a planet may be deflected, its path bent like a twig in a stream. Over millions of years, small forces accumulate. Encounters with stars, the slow tug of galactic tides, even the faint push of sunlight on dust. These processes stretch an orbit, tilt it, shift it, until one day the body drifts into new regions. For interstellar comets, this means leaving one star system and wandering into another. Atlas, in this sense, was not simply passing by. It was completing an arc written across unimaginable distances. Yet here we must acknowledge our limits. We can only reconstruct part of its path. Its faintness, its fragmentation, and its short window of visibility left uncertainties. We do not know precisely where it came from, nor what systems it may have brushed past on the way. Absence of this knowledge is not absence of history. It is only a reminder that some archives are too faint for us to open fully. Still, the orbit of Atlas left indirect clues. Its inclination, how steeply it crossed the plane of the planets, suggested an origin outside the solar system's usual reservoirs. Its high velocity confirmed it was not bound to the sun. The shape of its hyperbolic path, recorded in observations, is itself a testimony, preserved in digital records like ink in an astronomical ledger. Each of these markers is a quiet reminder of its greater journey. Let us now rest with a thought experiment. Step 1. Imagine Atlas forming near a distant star, orbiting it for millions of years. Step 2. A gravitational encounter, a passing star or a giant planet, nudges it free, setting it adrift into interstellar space. Step 3. After drifting for eons, it is drawn gently into our solar system, curving past the sun, disintegrating, and then vanishing into dust. In this sequence, its orbit becomes a
Thread connecting three epochs: origin, exile, and dissolution. Or let us picture another chain. Perhaps Atlas did not form in one system at all, but in a chaotic cluster where many stars were born together. In such environments, bodies may be exchanged freely, captured and released, their orbits rewritten many times. In that imagining, Atlas's trajectory is not a line from one place to another, but a record of wandering through many gravitational hands, its final path toward us only the most recent in a series of releases. From here, we soften into a pause. The orbit of Atlas was more than numbers on a chart. It was a trace of movement across time and distance, a thread stretching beyond our ability to follow. We cannot know its full story. We can only read the small part written in our sky. Yet even this part is enough to remind us that every path is an archive, every curve a memory of forces felt, every crossing a fleeting moment of visibility. Atlas has gone, but the trace of its orbit remains, preserved in quiet records, marking that for a short while, a traveler from far away passed through our neighborhood of the cosmos. What if Atlas was not only a comet passing briefly through our sky, but also part of a broader rhythm of celestial visitors that return again and again, shaping quiet patterns in Earth's history? When we look at single objects, they seem like isolated events, flashes that appear and fade. But when many such events are collected, we begin to notice cycles, regularities that hint at deeper structures. In astronomy, these rhythms often reveal themselves in archives, not only in the heavens, but also in the layers of our own planet. Each passage leaves traces, some faint, some lasting, and together they build a larger memory than any one object could carry. To place ourselves in this scale, let us think of time not in years, but in ages. Comets have visited Earth since its beginning, carrying ice and dust. Some strike, leaving craters and spreading debris. Others pass quietly, leaving only a faint trail of dust that becomes a meteor shower centuries later. In both cases, the memory is not lost. Rocks remember impacts. Ice layers remember unusual particles. Even cultures remember, recording unusual lights in the sky. Atlas belonged to this long rhythm, even if its trace is still hidden from us. Now we pause with the processes that preserve such rhythms. Sediments on the seafloor collect microscopic particles year after year. Ice cores trap tiny grains and gases, recording chemistry of the air at the time they fell. Even tree rings sometimes show anomalies caused by cosmic dust or atmospheric changes. These archives act as calendars far deeper than our written history. Scientists can read them layer by layer, like pages of a book, and sometimes they find peaks, thin horizons rich in extraterrestrial dust, unusual isotopes, or rare metals. Each horizon hints at a time when something arrived from the sky. We must pause here to notice our limits. Linking a specific comet to a layer in Earth's record is difficult. Dust disperses, signals overlap, and many processes on Earth can mask or erase delicate traces. Atlas in particular left no clear layer we can point to. Its dust may yet be out there, too diffuse for us to notice, or still drifting in space. Absence of confirmation does not mean absence of contribution. It means the rhythm may be slower than we can measure in a single lifetime. Still, the rhythm leaves indirect signs. Meteor showers return annually, each tied to a comet's orbit. The Perseids to Swift-Tuttle, the Leonids to Temple-Tuttle. These cycles are living archives, reminding us that comets are not random but recurrent. If interstellar visitors like Atlas come more often than we once thought, they too may form a broader pattern, one not yet visible to us, but perhaps measurable in the future, when more such travelers are recorded. Now let us imagine a thought experiment. Step 1. Atlas breaks apart, scattering dust into a wide stream. Step 2. Over centuries, Earth's orbit intersects this stream once in a long while, producing a meteor shower too faint to notice at first. Step 3. Thousands of years later, as the stream becomes denser, the shower grows brighter, and cultures yet to come may record it in their skies, unaware of its origin in a comet that disintegrated long before. Or let us imagine another sequence. Perhaps Atlas was one of many such visitors, each arriving once in an age, their dust combining into faint enrichments in Earth's sediments. Over millions of years, these enrichments form a rhythm, a repeating rise and fall in the record. Scientists in some future time may trace these layers, noticing the pattern of interstellar dust arrivals, seeing not individual events, but the long beat of a cosmic cycle. From here, we soften toward a pause. Atlas may never leave a distinct marker in our archives. Its dust may disperse too widely, its fragments too small. Yet even in this, it participates in the rhythm, the quiet, patient cycle of comets arriving, scattering, and fading. The rhythm is older than us and will continue long after us. Whether Atlas becomes part of a measurable cycle or remains only as a single faint note, it reminds us that every visitor belongs to a larger music, one written not in moments, but in ages, carried in dust, in stone, and in silence across the deep time of earth and sky. What if the silence of Atlas, after its brief glow, can be understood not only through telescopes, but also through archives we keep on Earth? Our quiet records of dust, of air, of faint signals collected over years. When a comet dissolves, its story does not end in the sky. Some of its traces fall unnoticed into our atmosphere. Some become invisible background noise in instruments. Some are preserved as unusual layers in ice or as faint enrichments in sediments. These fragments do not announce themselves. They wait, folded into the long patience of Earth's memory. To place ourselves gently in this frame, let us think of data as a kind of sediment. Each observation adds a layer, just as each snowfall on a glacier adds to the ice. A telescope log records the brightness of a comet on one night. A detector measures a faint chemical line. A satellite notices an extra wisp of dust. Alone, these are thin, fragile entries. Together, collected across decades, they form an archive that can be read like rings in a tree. Atlas is now gone, but its short presence has already been folded into such data, awaiting careful comparison with other visitors, other nights. Now let us pause with the processes that preserve these archives. Ice cores from Greenland and Antarctica hold tiny grains of extraterrestrial dust, trapped in snow that fell centuries ago. Ocean sediments collect micrometeorites, each carrying chemistry older than Earth. Instruments in orbit count faint flashes of meteors entering our atmosphere, logging them into statistical records. None of these alone confirm Atlas's passage, but together they form a net, capable of catching patterns too broad for a single observation. The archives are not loud. They are quiet shelves filled with fragments, patiently waiting. Yet here we must notice the limits. Atlas's dust may have been too sparse to leave any measurable layer. Its fragments may have burned too high in the atmosphere to reach ice or ocean. The comet may leave no unique signal, blending into the ordinary background of cosmic dust. Absence of detection does not mean its story is erased. It means only that the archive it left is one we cannot easily separate from others. Still, the language of archives leaves us indirect signals. The timing of atmospheric meteors may shift slightly when Earth crosses a new trail of dust. The chemistry of a layer may show enrichment in isotopes linked to interstellar matter. Long records of sky brightness may reveal subtle changes after a comet disperses its dust. Each is small, each uncertain, but together they hint at a wider story. A story that may include Atlas, folded invisibly into Earth's long record. Now
Imagine a thought experiment. Step 1. Atlas scatters a thin veil of dust across Earth's orbit. Step 2. Centuries later, fragments of this veil drift into our skies, entering the atmosphere as faint meteors unnoticed by most eyes, but recorded in sensitive detectors. Step 3. Researchers studying the statistics of meteor rates notice a small recurring peak. They trace it back to a comet long vanished, reconstructing its presence from archives alone. Or let us picture another path. Perhaps Atlas left no dust on Earth at all. Instead, its fragments dispersed into the broader zodiacal cloud, the diffuse haze of particles that brighten our twilight skies. In that case, the only record of Atlas lies not in ice or stone, but in the background glow we see without naming it, folded into the collective memory of many vanished comets. From here, we soften into a pause. Atlas is no longer visible. Its fragments have faded. Yet its presence endures, quietly, in archives of light curves, in scattered dust, in the statistics of meteors, in the slow layers of Earth's memory. We cannot read its full entry yet, but we can trust that nothing in the cosmos is ever truly lost. All is folded into larger archives, waiting for us to learn new ways of listening. Atlas, in this sense, still lingers. Not in a blaze, but in patient silence, part of the quiet record of sky and stone. What if the faint life of Atlas in our instruments was only the smallest visible part of a much wider phenomenon, one that quietly blends with the steady background of cosmic dust and faint light? When comets dissolve, they do not vanish completely. Their particles disperse, joining larger reservoirs of matter already drifting through the solar system. This diffuse haze, called the zodiacal cloud, is visible to us as a faint band of light along the horizon just before dawn or just after dusk. It is not a sharp trace, it is a background, a long and patient accumulation of countless small visitors. Atlas, though fragile and brief, now belongs to this continuum. To place ourselves in this frame, we may think of the sky as a room filled with floating dust, lit by a lamp. Some motes are large enough to see individually, sparkling as they pass the beam. Others are too small, too many, blending into a haze that softens the light. In the solar system, comets like Atlas are those brief sparkles, and their remnants the haze. Over millions of years, they accumulate, smoothing out into a background glow that tells us of past arrivals, even if it cannot name them individually. Now we pause with the mechanisms. Solar radiation pushes dust outward. Gravity pulls it inward. Collisions grind it smaller. Slowly, the balance is reached, a haze that encircles the sun. Sensitive instruments can measure its brightness, its density, even faint variations across the sky. These variations are the fingerprints of past comets. Each disintegration, each release of dust adds to the cloud, changing its structure subtly. Atlas, by breaking apart, gave its contribution. We cannot trace it directly. We can only say that its matter is now dispersed, indistinguishable from the broader background. Here, we must rest with uncertainty. No detector on Earth or in space can yet separate which particle came from which comet. The zodiacal cloud is too mixed, too blended. Absence of specific identification does not mean Atlas's dust is not there. It means only that its trace is dissolved into the collective archive, like a drop of water lost in the sea. Still, this archive has its language. Small variations in the glow at different wavelengths tell us about the size of the grains. Shifts in brightness across the seasons tell us about their distribution. Occasional surges hint at fresh additions from recent disintegrations. In this sense, the background glow is not silence, but a quiet murmur, a record of many dissolutions. Atlas is one of them, even if we cannot hear its voice alone. Let us try a thought experiment. Step 1. Atlas breaks apart, scattering dust into space. Step 2. Over months, radiation pressure pushes this dust outward, dispersing it until it blends
The zodiacal cloud. Step 3. Thousands of years later, the haze observed from Earth is a fraction brighter, a fraction denser, its balance shifted by the contributions of many such comets. Atlas is not forgotten. It is absorbed into the background, still present, but no longer separate. Or let us imagine another chain. Suppose that interstellar comets like Atlas arrive more often than we think. Each one breaks apart, feeding dust into the zodiacal cloud. Over millions of years, this cloud becomes a mixture not only of solar system debris, but also of matter from other stars. In this imagining, every twilight sky we see contains whispers from beyond, carried in faint light scattered by dust that once belonged to distant systems. From here, we soften toward a pause. Atlas is gone as a visible comet, but it is not erased. Its matter remains, dispersed into the background, folded into a quiet haze we see each dawn and dusk. The zodiacal light is a reminder that nothing in the cosmos is lost completely. All dissolves, all blends, all continues as part of something larger. Atlas has become part of that larger background, its story not ended, only absorbed into the collective memory of light and dust that fills our skies. What if Atlas, in its quiet disintegration, was not just a fragment of matter, but a messenger of timing, arriving when our instruments were just advanced enough to notice, yet still too limited to capture every detail? In astronomy, timing often matters as much as distance. We can only observe when an object crosses our sky, and we can only record what our tools of that era allow. Atlas appeared at a moment of growing interest in interstellar objects, after Oumuamua had passed and before we had built dedicated systems to detect more. Its story is therefore not only about its own material, but also about the way our observation windows shape what remains in memory. To place ourselves in this scale, let us think of an event like a passing echo. If we stand in a canyon and call out, sometimes we hear a long reverberation, sometimes only a faint return. The difference lies in timing, our position, the surfaces, the delay. With comets, the same applies. A bright one appears when our sky is clear and instruments ready. A faint one dissolves during poor weather or when attention is elsewhere. Atlas fell somewhere between. It was observed widely, but not closely enough. Its disintegration outpaced our ability to focus. The echo returned, but only faintly. Now we pause to rest with the mechanisms of timing. Modern sky surveys scan wide areas, but their coverage is not continuous. Gaps exist in cadence, in sensitivity, in follow-up. Atlas was detected by one such survey, its name itself a record of that system. Yet its brightening and collapse occurred faster than the interval between deep observations. By the time telescopes turned again, it was already dispersing. Timing shaped the archive, what we know, and equally, what we missed. Here we must pause with our limits. We cannot rewind the sky. No archive allows us to revisit what telescopes did not record. Absence of images or spectra does not mean the event was unremarkable.
It means only that our attention for those weeks was not finely tuned enough to catch every stage. Atlas leaves us with partial sentences in its diary, some words legible, others faded. Still, the language of timing has indirect traces. The fact of discovery at all shows that our systems now catch objects fainter than previous generations could. The pace of its fading reveals that its disintegration was unusually rapid. The clustering of observations around certain dates tells us more about human schedules than about the comet itself, reminding us that the archive of the sky is shaped both by nature and by us. Now let us try a thought experiment. Step 1. Imagine Atlas arriving 50 years earlier, before modern surveys. Perhaps it would have passed unseen, its fragments dispersing without record. Step 2. Imagine it arriving 50 years later, when
Interstellar trackers might already be in orbit. In that case, its chemistry could have been measured, its dust collected. Step 3. In our actual moment, it arrived in between, leaving only faint records. Its legacy becomes a marker of transition, not a fully read story, but a hint of what future archives may capture more completely. Or let us imagine another chain. Suppose Atlas's arrival coincides with a rare global effort, telescopes coordinated across continents, satellites aligned. Its disintegration would then be documented in exquisite detail. The timing would turn its fragility into a rich archive. Instead, its moment was quieter. Yet even in this, it serves as a reminder that the cosmos does not adjust to our readiness. Objects come and go according to their own clocks. From here, we soften into a pause. Atlas teaches us not only about comets, but about observation itself. Its timing was imperfect for us, yet still enough to leave traces. We cannot know all it carried, nor all it revealed. But we can see it as part of a longer rhythm, where each visitor is caught slightly better than the one before. Atlas's echo is faint yet meaningful, reminding us that even partial records shape the archive. The cosmos moves at its own pace. Our role is to listen, patiently, knowing that each arrival is both a presence and a rehearsal for what we may one day hear more clearly. Let us now imagine a thought experiment. Step 1. Atlas fragments, its pieces scattering along its orbit. Step 2. Earth, centuries later, crosses this orbit, encountering dust streams that spark faint meteor showers, unremarkable yet persistent. Step 3. Some of the grains fall into our atmosphere, a few reaching ice. And sediments. Thousands of years later, a scientist drilling a core finds a thin layer enriched with interstellar signatures. Atlas, long forgotten, would still be present in that quiet record. Or we might imagine another path. Perhaps Atlas's dust never reaches Earth, dispersing instead into the zodiacal cloud. In that case, its fragments become indistinguishable from those of other comets, contributing not a unique signal, but part of the steady twilight glow seen by every generation. In this imagining, its memory is not in separation, but in joining, a dissolving into the collective haze. From here, we soften into a pause. Fragility in the cosmos is not failure. It is one of the ways that memory is written. Atlas did not survive intact, but it did not vanish. Its matter was transformed into smaller pieces, its traces scattered into wider archives. We may not yet know where those traces will reappear, in meteor showers, in sediments, in faint twilight light, but we can be certain that its story continues. Dissolution, too, is a form of endurance, a quiet persistence across time. Atlas has become part of that persistence, a reminder that even in breaking, an object may leave its longest legacy. What if Atlas, in the way it appeared and disappeared, was less an isolated event and more a faint rehearsal of how we might one day study many such visitors with patience and precision? Each comet that passes, whether from our solar system or beyond, adds not only its own traces, but also teaches us something about how to listen better, how to refine our instruments, how to prepare for the next. Atlas was fragile, faint, and incomplete in the records it left. Yet even in that incompleteness, it helped shape the path of future archives, nudging us toward deeper readiness. To place ourselves in this context, let us think of practice. When we try to capture a fleeting bird in a photograph, the first attempt may be blurred, the wings indistinct. Later, after learning the patterns of its flight, we adjust. The second image is clearer, the third sharper. Astronomy, too, works this way. Each comet is a passing subject. We may not catch all details at first, but each missed detail tells us where to look more carefully next time. Atlas, in dissolving, revealed where our gaps remain. In chemistry, in timing, in rapid response observation. Now we pause with the mechanisms of how archives are shaped. Scientific records do not come whole. They are built layer by layer. Photographs, light curves, spectra, meteor counts, each adds a fragment. Later, patterns are stitched together. In the case of Atlas, many of these fragments were partial, interrupted by its sudden fading. Yet even partial records have weight. They remind us of the need for coordinated efforts across observatories, of instruments ready to act within days, not weeks. They remind us that fragility itself can be archived if we learn to move quickly. But we must acknowledge our limits with care. We cannot return to Atlas. We cannot build an archive retroactively. The comet's brief life in our skies is finished. What remains is not the object itself, but the questions it left behind. Absence of answers is not proof that none exist. It is a marker of timing, of opportunity missed, of lessons still unfolding. Still, the language of preparation is present in its wake. Telescopes are being redesigned to scan wider, faster. Data pipelines are being tuned to flag unusual brightening sooner. Space missions are being imagined to intercept the next interstellar visitor. These are indirect legacies of Atlas, not dust or gas, but shifts in how we think and how we listen. Its dissolution became part of the blueprint for future observation. Let us try a thought experiment. Step 1. Imagine Atlas arriving again, not in 2020, but in a decade when telescopes can scan the whole sky every night in greater detail. Step 2. Its brightening is flagged instantly. Spectra are taken before it breaks, chemistry recorded. Step 3. As it fragments, small probes already in orbit intercept the dust, collecting samples. Its story, once faint, is now recorded fully. In imagining, the difference lies not in the comet, but in us. Or let us imagine another sequence. Perhaps future interstellar visitors will be larger, brighter, more durable. With archives shaped by Atlas, we will be ready to record them in detail. The memory of what was missed will become the guide for what is captured. In this way, Atlas becomes a rehearsal, a soft lesson written not in permanence, but in absence. From here, we soften toward a pause. Atlas did not give us everything. It gave us fragments, fleeting signals, unanswered questions. Yet even fragments have meaning. They prepare us, they guide us, they teach us patience. The comet is gone, its dust dispersed, but its place in the archive remains, not as a full story, but as a reminder that even incompleteness is part of knowledge. We do not always need clarity to learn. Sometimes the faintness itself is what points us forward, quietly showing us how to be ready for what comes next. What if Atlas, in its fragile passage, was not only a solitary visitor, but part of a larger stream, a hidden current of interstellar matter flowing quietly through our system? When we think of comets, we often picture them one by one, each with its own orbit, its own brightening, its own fading. But in the vastness of time and space, objects rarely travel entirely alone. They are shaped by the same environments, nudged by the same forces, sometimes born from the same collisions or dispersals. To imagine Atlas as part of a wider migration is to soften the boundaries between individual and collective, to see not only a lone traveler, but a faint trace of a caravan passing beyond our sight. To place ourselves in this scale, let us think of the sky as a sea. A single wave may draw our eye, curling briefly before it breaks. Yet each wave is not separate. It is part of the tide, shaped by deeper currents. In the same way, Atlas may have been one crest of a larger flow, an interstellar tide of icy fragments that sometimes intersect our skies. If so, its story belongs not only to itself, but to the rhythm of many arrivals. Now let us pause with the mechanisms that might create such streams. In star-forming regions, where many suns are born close together, gravity pulls and scatters debris. Some comets are trapped, others released, drifting into interstellar space. Over millions of years, these fragments may travel in roughly similar directions, forming a loose stream, like dust carried by wind. If Earth crosses such a stream, we might see not one comet, but several over centuries, each faintly echoing the others. Atlas, alongside Oumuamua and others yet unnamed, may hint at such a pattern. Yet here we must pause with uncertainty. The number of interstellar comets observed is still very small. With only 2 or 3 clear examples, we cannot yet trace a stream. The apparent clustering may be coincidence or a bias in our detection. Absence of clear evidence does not mean the stream does not exist. It means only that the pattern is still too faint to confirm. Still, the language of possible streams leaves quiet signs. Similar velocities, similar orbital inclinations, or repeating directions in the sky may hint at shared origins. Statistical records, as they grow with each new detection, may reveal clusters rather than randomness. Even the chemistry of their ices, if one day measured, may show shared signatures, like regional dialects in a language. These are markers, subtle but patient, waiting to be read. Let us rest with a thought experiment. Step 1. Imagine Atlas not as one body, but as part of a swarm of fragments released from a distant star system. Step 2. Over millennia, the swarm stretches into a stream, thin but long, drifting quietly through the galaxy. Step 3. Earth, during our own small moment, intersects this stream, encountering first Oumuamua, then Atlas, and later others. To us, they appear separate, but to the stream, they are one continuum. Or let us picture another path. Perhaps interstellar streams are not rare, but quiet.
Common, each one the residue of past collisions. If so, then every few centuries, Earth may meet one fragment, each unnoticed link part of a much larger chain. Atlas, in this imagining, is not a singular event, but a whisper of a wider migration. From here, we soften toward a pause. We cannot yet say if Atlas belonged to a stream or if it was a solitary traveler. The evidence is too thin, the archives too brief. Yet the possibility itself opens a broader view, that what seems singular may in truth be collective, that each faint visitor may belong to a larger rhythm of arrivals. Atlas has gone, its fragments dispersed, but its presence still invites us to listen, not only for single voices, but for the murmur of many, drifting quietly across the galaxy's tides. What if Atlas, fragile and fleeting, was not merely a fragment from beyond, but also a quiet reminder of how little we truly know about the fabric of interstellar space? When we look at the night sky, it feels still, dotted with stars fixed in familiar constellations. Yet space is not empty, and it is not static. It is threaded with flows of dust, clouds of gas, and fragments like Atlas, moving unseen until they intersect with us. In this sense, each comet from beyond is not only a body, but also a probe, a particle of information carried across the galaxy, whispering of conditions far from our reach. To place ourselves in this context, we might picture the galaxy as a great library. Most of its shelves are beyond us, unreadable for now. But occasionally, a page is torn loose by chance and drifts into our hands. Atlas was such a page. Fragile, incomplete, perhaps missing whole sections, but still a piece of the larger book. What it told us is fragmentary. What it hinted at may be far larger. Now we pause with the processes that shape these hints. Interstellar space holds dust enriched with heavy elements forged in ancient stars. It carries molecules broken by radiation and ices preserved in deep cold. When fragments like Atlas arrive, they bring samples of these environments. If we could capture them, we might learn about chemistry in other regions of the galaxy. Instead, Atlas broke apart too quickly. Its contents were dispersed before they could be measured. Even so, the timing of its brightness, the arc of its fading, the shape of its tail, all these were indirect signals of what lay within. Here we must linger on our limits. We have only a handful of interstellar visitors recorded. Each one is unique, each one incomplete. Oumuamua gave us no dust, only a strange trajectory. Atlas gave us dust, but no long survival. Absence of complete evidence does not prove these are rare. It only shows how small our sample is, how new we are to this work. The quiet lesson is not that we know, but that we are just beginning to learn. Still, the language of traces leaves us paths to follow. Spectra of Atlas hinted at ordinary volatiles, water, carbon compounds, yet its fragility suggested a looser structure than many solar system comets. Its orbit confirmed its origin beyond. The combination is a marker, a body shaped in another system, built of familiar ingredients but bound more lightly, as though formed under different pressures or histories. These are clues, fragments of a wider picture still hidden from us. Now let us imagine a thought experiment. Step 1. Suppose Atlas was one of many such fragments passing every century, most unseen. Step 2. With instruments yet to be built, we begin to catch not 2 or 3, but dozens, measuring their chemistries, comparing their structures. Step 3. Over time, a pattern emerges. Differences in dust, in ice, in fragility, painting a map of the galaxy's diversity. In this future archive, Atlas would be remembered as an early, faint data point, part of the beginning of the map. Or let us picture another path. Imagine that interstellar comets like Atlas are remnants of ancient disruptions, planets breaking apart, collisions scattering debris. If so, then every fragment that reaches us carries a whisper of lost worlds. The dust trails, faint though they are, become archives of vanished systems. Atlas, in dissolving, may have been part of such a memory, even if we could not read it fully. From here, we soften toward a pause. Atlas is gone. Its fragments are scattered, invisible in the haze of space. Yet its passage reminds us that interstellar space is not empty, and that every faint visitor is part of a wider archive, waiting for us to learn how to read it. We cannot yet hear the full story, but even silence has meaning. Even incompleteness is part of the record. Atlas remains as a reminder that what arrives from beyond carries more than itself. It carries the galaxy's quiet history, folded into dust and ice, drifting patiently across the dark. What if Atlas, faint in its end and fragile in its passage, was not meant to be understood as a single mystery solved, but as part of a longer rhythm of learning, a rhythm that reminds us that the cosmos reveals itself slowly, in fragments, across generations. When we think of endings, we often expect closure, a final answer. Yet in astronomy, and especially in the study of visitors from beyond, endings are rarely final. They are pauses, openings to questions that will be taken up again, perhaps long after we are gone. Atlas leaves us not with certainty, but with an invitation to patience. To place ourselves in this perspective, let us think of a long story being told by many voices. One speaker begins, then fades. Another continues, adding details. The thread is not broken, only passed along. Comets are such voices. Some speak brightly, others faintly. Some carry clear words in spectra and dust, others dissolve before they can be measured. Atlas was one such voice, quiet, brief, incomplete. Yet its contribution belongs to the larger story of interstellar matter and the slow unfolding of the galaxy's memory. Now we pause with the processes of how endings become beginnings. When a comet breaks apart, its fragments disperse into streams, into clouds, into invisible haze. These, in time, may become meteor showers, or may settle into sediments on distant worlds. A disintegration is not an erasure. It is a transformation. What seems like an end from our viewpoint may, in cosmic terms, be a continuation in another form. Atlas, though gone as an object, persists as dust, as faint records, as a stimulus for the questions we now carry forward. But we must linger with our limits. We do not know how many interstellar fragments pass unnoticed, nor how many will come in centuries ahead. Our records are brief. Our archives are incomplete. Absence of complete data does not mean absence of meaning. It means only that we must live with the partial, with the fragmentary, with the gentle uncertainty that is the texture of much of science. Still, the language of traces remains. Light curves, archived in databases. Observations made from backyards as well as observatories. Papers noting its brightening and fading. Even the silences after its disappearance speak, reminding us of its fragility. These are the long-term residues, the faint layers in the scientific record, where Atlas is preserved. They are modest, but they endure. Let us imagine a thought experiment. Step 1. Centuries from now, as instruments grow sharper, archives of faint objects grow rich. Step 2. Scientists compare many interstellar comets, discovering patterns that were invisible to us. Differences in chemistry, in structure, in survival. Step 3. Atlas appears in those records not as a puzzle, but as one of the earliest entries, a faint marker of how the work began. Its incompleteness becomes part of a larger completeness, only visible across time. Or let us picture another chain. Suppose some of Atlas's dust survives to drift for millions of years, eventually falling onto another planet, perhaps into the soil of a world not yet known to us. There, its fragments may one day be studied by others, becoming evidence not only of interstellar matter, but of how far such matter can travel. In this way, its story continues beyond even our horizon. From here, we soften toward a close. Atlas does not give us certainty. It gives us fragments, hints, traces. It reminds us that the cosmos is too vast to yield its secrets quickly, that each visitor is both an answer and a question. Its end was quiet, but not empty. Its record is faint, but not lost. Atlas remains with us, in the haze of dust, in the quiet twilight light, in the patient archives of science. It is a reminder of scale, of time, of our place in a story far larger than ourselves. And as we rest with that thought, let us remember that the cosmos will continue to send its quiet messengers, and that we too are part of this rhythm, listening, recording, passing the story along. If we find calm in this slow unfolding, if we find resonance in this gentle pace, we already know how to continue.